Welcome back to Math 1300, Nunez Community College. Today we'll be talking about section 3.2, which is transformations of the graphs of functions. In the last video, we discussed the 7 basic function graphs and we drew them and showed how to plot them. Today we're going to do transformations on them, which means to move them and flip them. The first thing that we have is going to be called a vertical shift. Vertical shift means to shift up or down, to shift up or down. And the way that we're going to do this is we have the function y equals f of x, some function. And if we take that function and we add a constant, add a number, we will shift that particular function up that many units. So if it was plus 1, it would shift the whole function up 1 unit. If it was plus 8, we'd shift the whole unit up, the whole function up 8 units. When I do the examples, I'm going to give an example, I'm going to give a particular function, and then I'm going to show the thing that we're trying to do, which in this case is vertically shifted up. So the function I'm going to use here is going to say f of x is equal to x squared plus 2. Now, for the first one and the first one only, I will also do f of x is equal to x squared. This x squared is called the mother function. It's the function that is standard that we use. This one is the transformation. The mother function, if I take it and use an XY chart, I know that I would have -2, -1, 0, 1, and 2. And when I plug the numbers in for the x here, I would come up with 4, 1, 0, 1, and 4. So that when we plot the basic function that we learned about last time, this would be the ordered pairs in which we would graph it. And this we talked about was in the shape of a parabola. Well, if we're going to do a vertical shift, this would take that function right there and move it up 2 units so that the origin would move up 2 units. So that the point 1, 1 would move up 2 units. -1, 1 would move up 2 units, and 2 and -2, 4 would move up 1, 2, 3, 4, 5, 6. We'll move up 2 units also. So the actual function in this case would be that function moved up that many units, up 2 units. This is a vertical shift. No matter which one of the 7 functions we would be using, it would look like the function itself or the mother function, and it would be moved one way or the other. This is a vertical shift up. We also have vertical shifts down. Vertical shifts down. So for a vertical shift down, it would be y equals f of x minus c. This would move it c units down. Notice the plus c is not within the function. The minus c is not within the function. So if I'm going to do an example, let's do an example of a absolute value. In this case, we would have f of x is equal to the absolute value of x minus 1. It'll bring the absolute value function down 1 unit. The absolute value function looks like a V at 0, 0, 1, 1, 2, 2, and so on and so on. So if I brought it down 1, it would start here. And then we'd have points here. And then points here. So that we would continue to make the absolute value shape, which is a V. Again, if you're looking at it and you don't know whether this brings it up, down, or in the next case we're going to talk about left and right, make yourself a chart, plug the numbers in. -2, -1, 0, 1, and 2. It would be what? the absolute value of negative 2 minus 1. Absolute value of negative 2 is 2. 2 minus 1, it would be 1. And again, 2 comma 1. Absolute value of negative 1 is 1, minus 1 is 0. Again, 1 comma 0. It would take every single one of these and it would shift it to where it's going to be transformed to. But this would be an example of a vertical shift down. So we have vertical shift up, where we take the function and we add c to it. We have the vertical shift down, where we take the function and we minus c from it. After vertical shift, we have a horizontal shift. Horizontal shift means to shift left or right. So for a horizontal shift, I might have y equals f of x minus c. F of x minus c. By the way, this f of x minus c would be on the outside. This would be vertical. If I want to make it horizontal, I would have to say f of x minus c, where the c is on the inside of the function. Where the c is on the inside of the function. This would bring the function to the right c units. And notice when it says minus, you think about, well, okay, on the number line, I'd be going to the left. But when you put the number in here to compensate for it, it actually goes opposite. It goes to the right. So if I have f of x was equal to the square root of x minus 2, that would take the square root function and it would move it to the right 2 units. So the square root function, which would usually start here, we would start right here and we would go to the right 2 units. If you're trying to plot it using the graph or the table, you got to remember that f of x equals the square root of x. We would use the numbers, what? 0, because the square root of 0 is 0, 1, because the square root of 1 is 1, and 4, because the square root of 4 is 2. You have to compensate for that by what you know is going to happen here. So if I was going to do this, x comma y, if I know it's going to move it 2 units to the right, I would start with 2 units to the right, which would be 2. I would start with 2 units to the right, which would be 3, and I would start with 2 units to the right, which would be 6. And if we plug those numbers in, 2 minus 2 would be 0, the square root of 0 would be 0. 3 minus 2 would be 1, square root of 1 would be 1. And 6 minus 2 would be 4, the square root of 4 would be 2. So you can see that it does indeed move it, each one of the points, 2 units to the right. 2 units to the right. Okay, just like a horizontal shift that goes to the right, if I have y equals f of x plus c, that would bring the whole function c units to the left. C units to the left. So if I had my example of f of x was equal to x plus 1 cubed, x plus 1 cubed, that would bring the whole thing to the left 1 unit. So it would be the cubed function, and it would be to the left 1 unit. So it would look like this. Brought to the left 1 unit. Again, you can make yourself a table if you prefer to when you're trying to graph it, but that's what happens. Now, we could have multiple transformations in one, a vertical and a horizontal shift. Suppose I had f of x was equal to the square root of x plus 2 minus 3. You may be given something like that and be asked, what is actually happening? Well, you would say that it's moved to the left 2 units and moved down 3 units. It would still look exactly like the square root function, but it's going to be brought to the left 2 units and down 3 units. So it would start right here, and it would be in the direction of the square root. All right, from here, we're going to have something called reflections. Reflections. And with the reflections, we're going to have a negative multiplied by the function. Y equals negative f of x. This reflects across the x-axis. Reflects across the x-axis. And an example for that one would be f of x would be negative x squared. Negative x squared. What that would do is that would take the parabola x squared, which faces up, and it would bring it facing down. This would be reflected across the x-axis. Reflected across the x-axis. Again, the negative is on the outside of the function. The negative is on the outside of the function. If we want to have another type of reflection, we would put the x on the inside, the negative on the inside of the function. See where we have vertical, adding and subtracting to the outside. Where we have horizontal, it's adding or subtracting to the inside. Vertical, up and down, reflecting across the x-axis. The negative is on the outside. If we went horizontal, which means instead of reflecting across the x-axis, we would reflect across the y-axis, we're going to put it on the inside. So y equals f of negative x reflects across the y-axis. Reflects across the y-axis. An example of that would be like f of x is equal to the square root of negative x. The square root of negative x. Well, you know it's going across the y-axis, so our numbers, instead of being 0, 1, and 4, would be 0, -1, -4. Square root of 0 is 0. This is the negative of -1, which is +1. Square root of 1 is 1. And this is the negative of -4, which is going to be +4. Square root of 4 is 2. So that would reflect it the opposite way across the y-axis. So again, vertical shift up and down, horizontal shift left and right, reflections across the x on the outside, across the y if it's on the inside. And that leaves us with one more transformation in order to do, and that transformation is called a vertical stretch or shrink. And with the vertical stretch or shrink, we are going to mess with the y values of the function. Mess with the y values of the function because the y values go up and down. So that's vertical. So on a vertical stretch and shrink, I have y equals c times the function f of x. C being some number. If c happens to be 2, I'll multiply the y values by 2. If c is 3, I'll multiply the y values by 3. If c is 1/2, I'll multiply the y values by 1/2, which makes them smaller. An example here might be something like y equals 2x squared. Y equals 2x squared. It would take the function, which is x squared, which is the parabola, and it would raise the y values to double their height. So we'd bring it up to here, which would be 1, 2 instead of 1, 1, because 1 squared would be 1, 1 times 2 would give me 2, and -1, 2. And it would raise it up instead of 2, 4, 3, 4, 5, 6, 7, 8. It would raise it up to 2 comma 8 and negative 2 comma 8, which would be in this area, but I don't have room to put it. So we would draw our parabola, but again, c times it raises the y values up by that factor. So 2 times 1 would give me 2, or 2 times 4 would give me 8. So vertical stretch or shrink stretches it, it makes it look skinnier or fatter, but what it's really doing is taking the y values and multiplying by that number. This concludes section 3.2. We'll see you at the next one.